so far we've learned how to use binary numbers to represent positive integers. So how do we represent negative integers? Well, an obvious approach is to use the most significant bit. If it's set to 1, it signifies that it's going to be a negative number. Okay. If it's a 0, then it's a positive number. Okay. So if you look at these two numbers, if we make arrangements like that, it's going to. So we basically set aside the most significant bit for signs, right? And so if you're looking at a signed hexadecimal number, if the most significant digit on the left is greater than 7, meaning that the most significant bit would be 1, then the number is negative. Right? For signed numbers, that's 2 bytes. 8A, C5, A2, 9D, these are all negative numbers because the most significant digit here, 8, C, A, 9, are all greater than 7. Okay. One of the interesting thing is that now, so if we're using take out a bit for you to be used for a positive or negative sign. So what we have left, we have only 7 bits left, right, to represent the value of a number. So let me illustrate it. So previously, if we're going to use 1 byte, right, 8 bits to represent some numbers. Okay, so from 0, 0 all the way to 1, 1, all ones, right? So that is equivalent to the decimal number 0, and that's equivalent to decimal number 255, which is 2 to the power, let's see, of 8 minus 1. Okay, so that's 255. Now, if we take out 1 bit, right? So all we have left is 7 bits to represent numbers. Okay, so now you are, let's say, from 0 to 55, there's a total of 256 numbers, right? Let's consider 0 as a positive number. Okay? So 256 divided by 2 is 128. So you will have from negative 128, right, all the way to 0, and then all the way to 127. Okay, so that's what a 8-bit signed binary number can represent. Okay, after you've taken out the most significant bit for sign. Okay, so for the for 1 byte, right? For signed binary number, it can represent number between negative 128 to positive 127. Okay. For a signed word, it's negative 32,768 to positive 32,767, etc. Okay, so now consider this. If we want to subtract 28 from 54, another way of doing this is to add the number 54 and a negative number 28. Then you get the same result, right? Now, the things I have not talked about is that I talked about how to use the most significant bit for signs, right? But how do you represent the value of a how do you represent the value of a negative number, right? So, for example, how do you represent negative 3? Okay. Let's keep things simple. I'm going to just use a 4-bit instead of a byte. Let's say we are using 4-bit to represent signed numbers, okay? So let's see. I want to, let's say, negative 3. So one way to do it, it's a negative number, so this is 1, right? That means it's a negative number. 3, if you look at, now you have 3 bits left. And you could say, okay, so I want to represent 3 like that, right? That's one way to do negative 3, but there's a problem with this. If you do it this way, the positive 3 would be like this, right? 0, 0, 1, 1. Okay? Let's say this is negative 3, this is positive 3. So if you add these two numbers together, it should be 0. Okay? Let's see whether that's 0 or not. 1 plus 1 is 0. You carry 1 over. 1 plus 1, 0. Plus 1, you get 1. You carry 1 over. And then you get 1. And then you get 1. Okay? And this is not 0. So that's not the right way to represent negative 3. How do we represent negative 3? So we use a technique called 2's complement. Okay? So let's see, we have a positive number represent 3. That would be 0, 0, 1, 1. So that would be positive 3 because the most significant bit is 0, so this is a positive number. 2, this is 3, right? How do you get negative 3? The so-called 2's complement is that you are going to flip every single bit in this number, including the sign bit, and then add 1 to it. Okay? So you're going to be, to flip all the bits of this 3, you're going to have 1, 1, 0, 0. And then you add 1. So you're going to add 1. So now you use this to represent negative 3. Okay? Let's add these two numbers together and see what the result is. Okay? 1 plus 1 is 0. You carry over 1. 1 plus 1 is 0. Carry over 1. 1 plus 1 is 0. You carry over 1. 1 plus 1 is 0, right? There's no more. This is we're talking about a 4-bit integer here. There's nothing to go beyond 4-bit. Now you result in 0. Now that's what you want, right? So that's 2's complement. The takeaway is that you flip all the bits and then add 1. And you will get the equivalent number as the positive number, but in negative, right? So these two numbers have the same absolute values. One is positive, one is negative. Now, another way that I want to show you why this is used to represent negative 3, you can look at it this way. So the place value here is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So you can say, well, this bit, right, represent negative 2 to the power of 3. Okay? And then you add this one, which is 1 times 2 to the power of 0, 1, 2, 2. Okay? And then you add 1 at the end, right? 1 multiply 2 to the power of 0. So 2 to the power of 3 negative would be 8. Negative 8. Negative 8 plus 4 plus 1. Now you have negative 3. So that's another way to look at 2's complements. Okay? So negative numbers are stored in 2's complements notation. It represents the additive inverse, meaning that a number n, right, if you have a 2's complement of the number n, you add the two together, it should result in 0. Now let's look at a byte, 1 byte, which is 8-bit, with the most significant bit as the sign, right? So for a number, let's say positive number 1, how do you get the negative 1? Step 1, reverse the bits. Now you reverse all the zeros to 1. And then you reverse 1 to 0. And then you add 1 to the value from step 1. You add 1 to it. Now you result in this. This means this is a 2's complement of 1. If you add 1 and the 2's complement of 1, you get 0. Okay? So now this just means that this represents negative 1. Now look at another example. Let's say we want to subtract this 2 signed numbers, 2 positive numbers, right? We subtract 1100, which is 12. We subtract 3 from 12, okay? So from here, you borrow 2, and then the 0 has nothing to borrow. You further borrow up here, right? And then 2 minus 1, you get 1. And then because you get borrow 1 and you still have 1 left, so 1 minus 1, you get 0. And then this one is gone, so you get 0. And then 1 minus 0 is 1. So this is pretty straightforward, right? So just this is the same as what we have done before, subtraction, right? Binary subtraction. What if I'm subtracting a bigger number from a smaller number, and it's going to result in a negative number, right? Now, this is going to be tricky because you need to borrow here, right? When you do 0 subtract 1, you need to borrow, right? But the rest of the digits to the left, it's all zeros. So there's nowhere to borrow, right? However, 5 minus 9 is the same as 5 plus negative 9. So what you need to do is that you are going to get the number 5 and then get a positive number 9, and then you obtain the 2's complement of positive number 9 to get the negative 9. And then you add the two numbers together, and then you will get the correct result. Okay? So this is number 5. This is number 9, right? This is 8 plus 1. That's 9. Okay? You're going to obtain 2's complement of 9, which is instead of minus, you turn that to plus. Okay? All you need to do is to flip all the bits and then add 1. So 0, 0, 0, 0 becomes 1, 1, 1, 1. 1, 0, 0, 1 becomes 0, 1, 1, 0. Plus 1 and you get 1, right? Now this number will represent negative 9. And if you add these two numbers together, you will end up with this number. Okay? And I'll tell you this number represents the number minus 4. And how do you know that is minus 4? So let's see. 1, 1, 1, 1, 1, 1, 0, 0. Okay. One, 1, okay. 6 ones and 1, 0. Okay. 1, 1, 1, 1, 1, 1, 0, 0. My assertion is that represent minus 4. So how do you prove that? Okay. What is a, let's see, the positive number 4. Positive number 4 would be 0, 0, 1, 0, 0, 0, 0, 0, right? Because this is this place value is 1, place value is 2, place value is 4. So that represents positive 4. So you add these two numbers together. 0, you carry over 1. 0, carry over 1. 0, carry over 1, 0. 1, 0, carry over 1, 0. Right? So now you prove this number is indeed negative 4. Now, there is a kind of a simple way of converting. So I have shown you how to convert a positive number to a negative number. And you can also convert a negative number to a positive number by doing exactly the same two's complement effort, two's complement method. For example, let's take this number, right? I want to obtain the positive 4. I'm going to first flip all the bits to 0, 0, 0, 0, 0, 1, 1. Okay? And then I add 1 to it, right? That becomes 0, 0, 1. 0, 0, 0, 0. Now, we know this number is 4, positive 4. So you can use the two's complement approach to obtain a negative value. And you can also use the same approach to flip a negative value to a positive value. Okay. So how do you form the two's complement of a hexadecimal integer? Okay, so one way to do it is that you can always convert hexadecimal number for each digit. You turn that into 4-bit binary number, right? And there is an easier way to do it, meaning that you can reverse all the bits and add. It's the same thing. You reverse all the bits and add 1. And an easy way to reverse a bit of a hexadecimal number is to subtract the digit from 15. For example, for 0, if it's in 4-bit representation, it will be 0, 0, 0, 0, right? F, which represents the number 15, right? It would be 1, 1, 1, 1. So to flip every bit in 0, it would be F. To flip every bit in 1, you will get E. To flip every bit in 2, you get D. To flip every bit in 3, you get C. And so on and so forth. Same thing, to flip every bit in B, you will get 4. Because you subtract, 11 from 15, you get 4, right? So here's some examples of hexadecimal integers converted to their two's complements. 6A3D, okay? 6 two's complements. You flip all the bit of 6, you get 9, okay? And then you get 9 here. You flip all the bits in A, you get 5, okay? You flip all the bits in 3, you get C. You flip all the bits in D, you get 2, plus 1. And then you get 95C3. 95C3 would be 2's complement of 6A3D. Now, 6A3D is a positive number because 6 is smaller than 7. And this is a negative number because 9 is greater than 7. But the absolute value of these two numbers are the same. It's just their signs are different. Okay. All right. So here is one more example. To look at another way to obtain a sign value is to assign a negative weight to most significant bit, right? And this is the example I showed you earlier to prove that the two's complement method is correct. That concludes this video.